Welcome to Air Academy Associates series on using SPC Excel. This video clip is part 2 of a 4-part series on control charts. In this video, we will address the topic of the Xbar R chart. As the name implies, Xbar means average or mean value, and R means range. Reviewing our control chart wizard in SPC Excel, we see that the Xbar R chart involves the concept of a subgroup. In part 1 of this series, we saw that an IMR chart was for individual values, and if we may call it this, a subgroup of size 1. With the Xbar R chart, we will be looking at subgroup sizes of more than 1. And as with the IMR chart, where we got 2 charts for the price of 1, namely an individuals chart and a moving range chart, in the Xbar R chart, we will also get 2 charts, the Xbar chart, which is a plot of averages, and the range chart, which is a plot of ranges. So what exactly is a subgroup? And these subgroups are typically called rational subgroups because it's a subset of data collected under relatively homogeneous conditions. Now, in order to get homogeneous conditions, subgroups are usually collected within a segment of time, like an hour, a shift, or a day. And if we're dealing with space, it could be a square yard or a square mile. It could be organizationally, different departments, different divisions, different medical centers, or it could be different product types. The purpose of getting data from a subgroup is basically twofold. First, to determine the variability within each subgroup. The key word is within. This will be shown in the R chart, where the ranges of each subgroup are plotted. Secondly, to determine the variability between the subgroups. The key word here is between. This will be shown in the Xbar chart where the averages of each subgroup are plotted. We would expect the within subgroup variation to be less than the between subgroup variation because of the homogeneity of the subgroups. And let's take an example to give you kind of a glimpse of what a subgroup really is. Let's say the practitioner should be the person who determines the scenario in which the variability within and between is desired. For example, suppose a hospital wants to determine if the performance measure of length of stay in days for some particular procedure is stable from a month-to-month perspective. It will then take sample data within each month to form a subgroup for each month. Subgroup sizes that are most common and typically used are from 4 to 6. It guarantees us that the X bars, or the averages that are plotted, will indeed come from a normal distribution, and if it comes from a normal distribution, we have the zone rules working for us. Let's take a look at the software and examine how we do an Xbar R chart. Let's suppose that a hospital monitors the average length of stay for patients undergoing open heart surgery. Data for the past year is given for 5 randomly selected heart patients each month. In other words, the subgroup size is 5, and we took 5 different values for each of the 12 months in this particular year. So the team wants to see if there are any trends in the data. Is the within month variability and the month-to-month variability of this data stable? So let's take a look at this. The way you do an Xbar R chart is, first of all, highlight the data. We don't highlight the labels of the columns, just the data itself with the x-axis label, which will be month here. Then we come up to control charts in SPC Excel. We come down to Xbar R chart. We click on that. Excuse me, and since we've already highlighted the data, there's no sense to specify what our labels are. We can just click through this, and then let's get the stacked charts, that is the Xbar and the R charts, on the same sheet. You can put them on separate sheets if you'd like, but when we examine the Xbar R chart, it's nice to have them stacked on the same sheet, and you will see that as we go forward here and get the charts. So here's the Xbar chart on top. This is the average value from January, February, March, April, May, as the horizontal axis indicates. You can see this process is pretty stable except for one data point, and that was February. The February data point, the average of the 5 lengths of stay in February was abnormally high, and that might precipitate an investigation of what we were doing in February that made it different from all of the other months. But in particular, there's no other symptoms shown here. In general, it's a fairly stable process except for this point right here, which deserves an investigation. To compare and contrast the IMR chart with the Xbar R chart, I'm going to revert back to some data that you all probably were involved in at some point in time in a course that involved shooting a miniature Roman catapult, which we called a statapult. And in this case, before the improvement took place, each of 7 operators took 3 shots on the statapult. And you can see their distances here, 85, 96, and so forth. So this is the baseline data. There are 21 data points. And before we do an Xbar R chart and give you the reason why we might do an Xbar R chart, let's review the individual with moving range chart. So we're going to build an individual with moving range chart here. This is going to be fairly easy, and we've seen this chart before. Let's get this a little bigger on the individuals chart here. Let's click on the axis and move that up to, let's see, we can go to 60, I believe, on this one because, yes, oops, that's a little bit too much. Let's go back down to 40. Okay, that'll show all the data points. And cut this off and we get the complete chart. Now, up here in the individuals chart, this is each individual data point. And you see a lot of red. If we go back up to the sigma zone, you'll see the out of control symptoms showing all. If we show the points that exceed the control limits, you'll see only that one in red and that one in red. If we show the ones that are the center line violations, you see a lot of data here entirely above the center line. You see a lot of data down here, at least 7 points in a row that are entirely below the center line. Again, lots of symptoms that indicate this process is not behaving with regard to just normal or natural variation in the process. There's a lot of special causes going on, a lot of variability, a lot of these symptoms are occurring. And you also have the Zone A rules, which are right down here, and you have the Zone B violations, which are right in here as well, and over here as well. So a lot of violations of our rules or of symptoms that show out of control behavior. Our range chart doesn't look too bad, the moving range chart. Remember, this is a moving range because you need 2 data points to find a moving range. So the moving range in an IMR chart is kind of like the range chart in an Xbar R chart, except that it is the difference between 2 consecutive points because our subgroups are basically of size 1. Now, examining this chart further, we see a point like this over here, and that's the 12th data point collected. And you say, well, which operator was that? Well, these 3 points right here came from the first operator. The next 3 came from a second operator, and these 3 came from a third operator. These came from a fourth operator, and so forth. So it's hard to detect from which operator these points came, but a way around that to look at operator variability, operator to operator, or between operator variability, and within operator variability would be to do an Xbar R chart. Let's go back to the raw data of this statapult data, and considering the fact that we had a natural subgrouping of 3 for each operator, which will allow us then to look at operator to operator variability as well as within operator variability, the Xbar R chart will provide us some convenience for doing that. So let's highlight the data. These are the 21 data points, the first 3 coming from one operator, the next 3 from a second operator, and so forth. So let's go to control charts and let's do an Xbar R chart on this data instead of an IMR chart. And let's finish it off. And notice that the software is going to ask you, when you have a data in columns like this, it's going to ask you, what is the subgroup size? In our case, it's 3, because each operator took 3 shots consecutively. So let's finish it, and here is our Xbar R chart. Xbar chart is up here, the R chart is down here. Again, this looks, what is that value? That's about a 64, so I think we can go down to about a 60 here. Now, 60. Let's see if that still stays in bounds, and it does. You can see this a little better here. Now we have 7 data points plotted in each of these charts instead of 21. But each data point represents, in the Xbar chart, an average of 3. And the R chart represents the range of 3 values here. The range chart looks fine. Everything seems to be fine. The Xbar chart notices and points out that 2 operators are considerably different. Operator 1 was considerably shooting higher at an 89 average than operator 4, which was shooting at a 64 average. So this seems to be an indication that we've got some differences, operator to operator differences, although the within operator, as exhibited down here from the R chart, does not seem to be much different from operator to operator. Now at this point in time over here, after these 21 data points, or 7 operators each shooting 3 launches apiece, an improvement event was taking place. So if you look at the data, this was the improvement after the improvement data after they made the process flow cause and effect with CNX and SOP improvements. And I've copied this data below the original column so that in one fell swoop I can update this chart. So I'm going to come up to Sigma Zone and update the chart because I have all the data now in one column. And you'll see that the process has indeed changed. Over here, these are your new 7 data points, and the range has been cut down significantly from what it was before. And clearly, this is a different process than this process right here. So we are going to split the control limits at point number 8, because that's the first of the next set of data. And we do that, and everything is so tight, the control limits are so close together you can barely see what's going on here. So what we're going to do is go back to the raw data, and we're just going to take the second set of data and look at that by itself. That'll allow us to blow it up a little bit more on the screen. So we're going to the Xbar R chart, and this is the second set of data, or the improved set of data. And the subgroup size is 3, and now we should be able to see it in a little bit bigger light, so to speak. There is operator 5 seems to be different because this operator is shooting on average very, very low. Now when we see a lot of data points that are the same on an Xbar chart like this, it's an indication that the resolution of the measurement system is probably a little lax, and they could have probably measured to maybe the nearest ½ inch instead of the ¼ inch. But nonetheless, this operator, operator 5 now, is pinpointed as having shot typically lower, 76-inch average compared to up here the higher, a 77.33. Now, keep in mind the upper and lower control limits are really tight, 77.4 inches down to 76.5. That's less than an inch. So the difference between the upper and lower control limit here is physically, in physical units, less than an inch. So that's not a whole lot, but that's the beauty of control charts. When the variation gets low, you're going to be able to detect some outlying data points. Now, if we look at data point 5, it's this 75 that's creating trouble. Okay, notice almost all the data is either a 77 or a 78 or a 75. That's the data point that is causing operator 5 to be out of control in the low realm. So let's suppose, for the sake of simplicity, we went back to the process and the operator says, oh yes, I know what happened on that shot. it slipped out of my hand. So let's go in and mark that guy as an outlier. When you mark a point as an outlier and you recompute the chart, notice I've done something to the raw data, and the chart is now saying you have not updated the chart. Now, when I mark a point as an outlier and I update the chart, it will change your control limits based on that missing data point. But it will always leave the point that is involved in the change of the control limit calculations in the graph itself. So if we update the chart, you'll see the control limits now got even a little tighter. It's almost about 0.2 of an inch with that data point, not that one data point. That was one data point. You still have an average there of 76.33, but that one data point, that 70, this point is still shown as before, but it was not involved in the calculation of the upper and lower control limits. Now look what happened. Without that point being looked at, this point right here now went out of control. So now that 78 is also out of control. So the bottom line is, if you don't want to see this point, you'll have to come in and actually remove it. So marking it as an outlier will not remove the point from the graph. What it will do is remove the point from the calculation of the control limits. If you want to remove the point altogether, you'll have to come in and blank it out. And then do, of course, then we can go back to Xbar. It says you can update the chart because you made a change in the data. So we update the chart and we say, yes, we want to do it. And now that data point is no longer there. We still see that data point that was involved, that 75 is no longer there. And this guy here is a 77 now. Why? Because all the three shots from that operator were 77, 77, and 75. The 75 has been removed, so that's what we get. So the beauty of the Xbar chart is it allows you to look at subgroup to subgroup variability. In this case, an operator formed the subgroup. An operator, we had a natural subgrouping of 3 per operator. So I hope that gives you a little bit of feel for what an Xbar R chart is. It's a very powerful chart, and thank you for watching.